Now we will discuss the non-ideal effect of BJT. In this topic we will talk about the 4 different subtopics, that is base width modulation, base width modulation, then breakdown. Second topic I will be talking about breakdown at collector junction, and fourth I will be talking about emitter band gap narrowing. So these are the 4 different topics I will be discussing. First, base width modulation. In base width modulation, we have already discussed many points earlier, but just recall of that. In base width modulation, what happens? You can see my previous videos where I discuss about the base width modulation in common base configuration of BJT. That was early effect. So in this is emitter, this is collector, this is base. I'll be a little amplifying the width of the base just for clarity purpose. This is suppose N type, this is P type, this is N type. Fine. So normally this is forward biased. This junction is this is emitter junction, this is your collector junction. So collector junction is normally reverse biased and emitter junction is forward biased. This is base. Fine. So when you inject the carriers, when it is forward biased, the electrons from this side will be injected into the base. So electron concentration at this point will be high. And if you talk about the depletion layer, it is having the width like this at the collector junction, and it is very narrow at emitter junction because it is forward bias. The width of depletion layer is larger at the reverse bias junction, it is small at forward bias junction. Fine. So when you forward bias the emitter junction, so a lot of carriers, that is electrons, will be injected into the base region, but through the base it reduces linearly and falls to 0 at the edge of the depletion layer like this. Fine. This is how it varies. And what happens when you further increase the reverse biasing voltage at collector junction? So width of the depletion layer will increase and this will penetrate this way. Your depletion layer width will penetrate into the base region, and now your this magnetic carrier concentration will fall to 0 at this edge rather than this. So concentration gradient will increase. That results into increase in emitter current, that results into increase in collector current, and so on. We have seen all these points, we have all discussed all these points in my previous videos. You can just see especially the common base configuration of BJT where I discuss about this. Fine. Now what is happening here is collector current is increasing with increasing VCB. Fine. If you recall, the output characteristic of BJT, it was something like this, something like this. So this is IC, this is VCE. If you extend these characteristics somewhere backward, you will find these will meet at certain voltage VA. Fine. This point VA magnitude is called early voltage, and this decrease in width of the base region due to increase in voltage VCB, reverse biasing voltage, is known as base width modulation. Fine. The collector current as a function of VA is given by VCE plus VA, where G naught is called output conductance of BJT. I will not discuss much about this effect because we have already discussed base width modulation is known as early effect. This results into decrease in base width, increase in concentration gradient in the base region, concentration gradient of minority carriers, increase in emitter current, increase in collector current, then increase in alpha, increase in beta, decrease in base current. All these points we have seen. Fine. There is important point that we will discuss in the next topic, that is breakdown voltage, breakdown of the junction. So for base width modulation I will be discussing this much because we have already discussed much about it in previous videos, that is in configurations of BJT. So second topic I'll be talking about is that is breakdown. In BJT, your emitter junction is forward biased. So there is no question of breakdown at forward bias junction. However, in case of normal active mode, it is forward biased, but when it is used as a switch, it is reverse biased in off condition. So at emitter junction, I apply reverse biasing voltage when BJT is operated as a switch to turn it off. So that voltage is limited by the breakdown voltage of the emitter junction. And we know emitter is heavily doped in BJT, base is moderately doped, collector is lightly doped. So emitter junction is heavily doped. When there is a junction between moderately doped and heavily doped emitter and moderately doped base, that junction will be having a mechanism of breakdown which is known as Zener breakdown. There are two types of breakdowns. One is called Zener breakdown, another is called avalanche breakdown. Zener breakdown occurs when both sides of the junction are heavily doped, which is emitter junction in this case. Zener breakdown is because of the breaking of the junction because of heavy electric field in the depletion region. The avalanche multiplication junction, but that happens because of the collision of the carriers with the atoms, collision of thermally generated carriers with the atoms, thermally generated electrons with the atoms. So that is known as avalanche multiplication. So both have different mechanisms of breakdown. So emitter junction has Zener breakdown mechanism, whereas avalanche is, this is lightly doped, this is moderately. So when there is a junction between lightly doped PN layers or lightly and moderately doped layers, there is a breakdown of the junction which is known as avalanche multiplication. So emitter junction has the Zener breakdown mechanism, collector junction has avalanche multiplication breakdown. But at collector junction there is another breakdown. That voltage between collector and base has two mechanisms of breakdown. One is your avalanche multiplication. There is second mechanism as well, that is known as punch through. What is that punch through? Let us see that. So there are two mechanisms of breakdown. There are two mechanisms of breakdown of what? Of collector junction, or you can BJT, breakdown of BJT. Let us see that. First I will be talking about is punch through. What is that punch through? Let us see this. I have not discussed this punch through phenomena till now. Punch through phenomena is basically related to the again voltage VCB. When you increase the voltage VCB, your depletion layer width will go on increasing and base width will keep on narrowing, and there may be the situation when whole of the base region is completely covered by the depletion layer at such a high voltage. When VCB becomes such a high voltage that the complete base region is covered by the depletion layer, that phenomenon is known as punch through. So punch through, I'm sorry, I'll take just 1 minute. So punch through is what? Punch through is basically the state where complete base region is occupied by the depletion region. Fine. When depletion region is completely occupied by when base region is completely occupied by the depletion region, there is no recombination in the base region. Your base current base current becomes zero. All of the carriers are reaching at the collector. So your transistor operation as an amplifier ceases to exist. There is no more amplifier operation when whole of the base region is covered by the depletion layer. That is the situation of breakdown. Your BJT is behaving no more like an amplifier. So punch through should never happen. So I hope the concept is clear. Now let us see the voltage. We know what is the expression of the width of depletion layer. You can see this is your collector junction. I'll again redraw it like this. This is your collector junction here. This is your base. This is your emitter junction. This is your collector junction. This is width of the depletion layer earlier. Fine. So this is base width, and this is the width depletion layer which is there on the base side, W dash you can say, or W, right? So width of the depletion layer is given by, that is, this is width of the depletion layer in base region. Depletion layer width in base region. Let us see that. Fine. So we will see the depletion layer width is given by W equal to 2 epsilon by Q into NC upon NB by NC plus NB into VCB. I am neglecting the built-in potential at this point. Fine. So this under root. So when the voltage VCB is equal to punch through voltage, that is large enough, whole of the base region, please remember, see this, whole of the base region will be covered by the depletion layer. See, your complete base width will be equal to the width of the depletion layer in base region. So 2 epsilon by Q into NC by NB into 1 by NC plus NB into the pinch of, that is your punch through voltage under. So this gives what? I can find the expression of punch through voltage. So punch through voltage Vp will be equal to, you can see, Q WB square by 2 epsilon into N B by NC into NC plus NB. That is your expression of the punch through voltage, and that is voltage at collector junction, voltage between collector and base junction. Expression of punch through voltage. When there is condition of punch through, what will happen? What will be the problem? If you remember, this is your layer diagram, this is your base. Fine. So in normal case, your energy band diagram is like this. When you forward bias, this side shifts upward, this side shifts downward. This is the normal band gap, your potential barrier. But when you reverse bias, this is VCB and this shifts upward by how much level? By VBE level, like this. Fine. But when there is condition, when there is basically punch through condition, what happens? When you go on increasing VCB, the width of the depletion layer will increase and this will be penetrating like this, and there may be the situation when there is condition of punch through like this, like this. This is how it is going to vary. And at the condition of punch through, you will find this junction barrier will remain V dash. What I mean to say is, at the condition of punch through, there will be decrease in potential barrier at the base emitter junction. That is how it happens. And emitter current will definitely increase because of the decrease in potential barrier. So these are some of the effects of your punch through condition, and this is the expression of punch through voltage. Please do remember the expression, there can be question. There is a second type of breakdown at the collector junction, which is nothing but avalanche multiplication. Avalanche multiplication at collector junction. So avalanche multiplication basically occurs due to the thermally generated electrons which are moving across the junction, and these collide with the lattice atoms in the depletion area, where these will be generating more electrons, resulting into breakdown, which is known as the avalanche multiplication. If you recall, we have the collector junction here. This is voltage VCB and this is voltage VCE. So there will be breakdown of this junction, but there is point to be observed here. At breakdown, when you have the breakdown voltage VCB, the breakdown voltage VCE in terms of VCB is given by B VCBO VCB divided by beta power 1 by n, or it is equal to B VCB by, and this is VCO, this is VCBO, by HFE power 1 by n. What is this VCBO or VCO? VCBO is basically, if you open the terminal, emitter terminal, find the breakdown voltage between base and collector, that is breakdown voltage VCB naught. Breakdown voltage VCB naught. You open now, second possibility, you open the base terminal, find the breakdown voltage between collector and emitter, that is VCEO. There is a relationship between VCEO and VCBO that is given by this. So what I find here is, when this emitter terminal is open, what is the current between this? That is called ICB naught. And when this is open, what is current here? That is called ICE naught. Fine. So if you see the relationship here, this is definitely more than approximately 100. So power 1 by n, and that is variation of n. So if you see, there will be two types of breakdown of the BJT. This is IC. So here, like this, this is voltage VCE, this will be nothing but VCB naught, this will be VCE naught. This current when base terminal is open is ICE naught, and this current when your emitter terminal is open, that is ICB naught. So this is how the breakdown occurs. So breakdown voltage when base terminal is open, breakdown will be at lower voltage as compared to when breakdown occurs when your emitter terminal is open. This is the relationship between these two voltages. As there can be one question in exam on this formula, especially in engineering services prelims, there can be one question on this diagram, but this is not very important topic, but this is how the relationship exists between the breakdown voltages. Just remember, at collector junction there can be two types of breakdowns. One is avalanche multiplication, second can be punch through. So we have seen the expression of punch through, and these are the expression of the breakdown voltages for avalanche multiplication. So this covers your breakdown mechanism. There are now two small topics which are not very important as far as the exam is concerned. One is called high injection. What is high injection? High injection is basically when you increase VB voltage, when your emitter current is increasing, when you are injecting large number of carriers from emitter side, there will be increase in concentration of the carriers in the base region, that is excess minority carriers. When excess minority carriers increases in the base region, correspondingly for neutralization of the carriers, the excess minority carriers in the base region will also increase. I repeat, when you inject carriers from emitter side, that is high injection. I'll be talking about the next topic, that is high injection. right? So in high injection, basically you have you inject large number of carriers from, that is, base side, emitter side to base. So when these carriers become minority carriers in the base region, but their concentration of carriers in the base. Suppose you have NPN transistor. When you inject electrons from emitter side, the concentration of electrons near the emitter junction can become more than the holes in the base region. So for neutralization of that, the concentration of holes near the emitter junction increases. Fine. That results into reduction in emitter injection efficiency. So this is just point to remember. High injection results into reduction in emitter injection efficiency. You don't need to go for the complete analysis for that. Another important point here is because of that there is variation in beta. Initially it increases, initially beta increases, then remain constant and again decreases. This is beta, this is collector current, and at high collector current this is because of high injection. The beta decreases because of high injection at high value of collector current. That is what I wanted to tell. Beta is not constant. Beta changes with collector current. Initially it increases, becomes almost constant, and then decreases. Then third is, fourth last one is known as emitter band gap narrowing. Again, this is not very important topic, but emitter band gap narrowing means what? When you increase the doping level in the emitter, when doping level in the emitter becomes very high, what will happen? When suppose you talk about NPN transistor. So in NPN transistor, emitter is N-type. So what is the impurity? Donor. So when you increase the donor concentration, what will happen? Initially, normally, if you talk about the band energy band diagram, this is EC, this is EV, and somewhere near the conduction band I have one level which is known as the donor level. When you increase the donor concentration, it will not be simply like this, rather it will form a band. It forms a band, and because of which overall band gap of the semiconductor reduces. That is known as band gap narrowing. Band gap narrowing also results into the reduction in emitter injection efficiency. Just remember just a point, otherwise there was no question in past as well as such. But when you increase the donor concentration, so donor energy level will not be discrete because of the interaction between the donor atoms like semiconductors. So that discrete energy level will split into the bands, and effective band gap will decrease, which results into the emitter injection efficiency. That's it. As far as example, I am not taking high injection and band gap narrowing into detail. Reason being you don't have question on this. Just for sake of coverage, I have covered this topic. There may be hardly one question in engineering statistics prelims, and it is not important at all from GATE point of view. Only these two topics, that is high injection and emitter band gap narrowing. Otherwise, base width modulation, punch through voltage, these are important topics for exam. And with this we finishes your BJT. So just wait for my next topic. We'll be starting with field effect transistors. Thank you very much for watching the video.